In this video, we're going to discuss ions. For the last few days, we've been reviewing grade 9 concepts. One of the concepts we reviewed were the categories or classes of elements in the periodic tables. We saw metals, metalloids, and nonmetals. And then we also saw that within those classes there are special groups of elements called families or chemical families. We saw the alkali metal, alkaline earth metals, halogens, noble gases. I do want you to know the important properties of the different classes and the different families as we discussed. You should be able to fill in blanks such as these ones over here. So you know that all the elements in group 1 are alkali metals except for one of them. Try to figure out which one that is. You know metals are typically solid at room temperature except for one. And I want you to focus on what gives elements their characteristics. So for example, why are all the alkali metals similar to each other? And you know that's because they have the same number of valence electrons, 1. And you know that noble gases, they're all similar to each other because they have the same number of electrons, 8 in the same number of valence electrons, 8 in the last shell. Alkaline earth metals are also very similar to each other because they have the same number of valence electrons. So the reason elements within a group are so similar to each other is because they have the same number of valence electrons. Not electrons total, but valence electrons. And that's what makes them react in a similar way towards other elements. So let's get down to the business of what an ion actually is. An ion is any atom that has a charge due to gain or loss of electrons. So an atom can gain or lose electrons, and when it does that, it's going to become charged. Usually, the atoms we've been talking about have the same number of protons and electrons. So for example, if we look at oxygen in the periodic table, oxygen has 8 protons, as you can tell from its atomic number. That's 8 positive charges. And also 8 electrons from its atomic number. That's 8 negative charges. The negative and the positive cancel each other out, and so you have a neutral oxygen atom. So if you change this number here of electrons, now the negatives and the positives won't cancel each other out. So let's go take a look at the 2 types of ions that exist. There are 2 types of ions. There are cations and anions. Cations are atoms that have lost 1 or more electrons. So for the purpose of this lesson, I want you to think of an electron like a negative thought. If you lose a negative thought, you become a positive person. So if an atom loses an electron or more, it becomes more positive. So cations are positive, and it's usually metals in the periodic table that form cations. Metals will lose electrons to become positive cations. Over here you can see Na+. This plus, there's no number next to it. We know there's a 1 there. Whenever you don't see a number next to a superscript, a small number on top, it's an implied 1. That plus there indicates that sodium lost 1 electron and became positive 1. Let's say, for example, we saw Ca2+. That means that calcium lost 2 electrons and became positive 2. Suppose we saw Al, or aluminum, 3+. That means that aluminum lost 3 electrons and became positive 3. The other type of ion is an anion. It's an atom having gained 1 or more electrons. So remember, electrons are negative thoughts. If you gain a negative thought, you become a negative person. So when atoms gain electrons, they become negative, or also called anions. And it's not the metals that become anions, but it's actually the non-metals that become anions. So non-metals gain electrons and become anions, which have a negative charge in the end. So you can see over here chlorine, Cl-, that indicates that chlorine gained an electron and now has a charge of -1. Over here, for example, if I have O2-, this means that oxygen gained 2 electrons and has a charge of -2. If I had N3-, this means that nitrogen gained 3 electrons and has a charge of -3. So to remember these terms, there's a few tricks you can use. Cation, if you spell the word out, the T in the middle looks like a plus, or some students who think cats are cute associate that with being positive. If you don't like cats, just don't use that trick. Anions, if you look at the word, it looks like a negative, A-N, a negative ion. And some students who hate onions say this word looks like the word onion, so it's negative. But again, if you love onions, maybe you shouldn't use that trick. And I do need to emphasize that ions are forming because the electron number is changing. You're either gaining or losing electrons. Protons are not going to change, and neither are neutrons. There should be no change in the proton number. So this oxygen over here that has a charge of -2, it still has 8 protons. That did not change. But because it has -2, what that means is it gained 10 electrons, or it gained 2 electrons. So now it has a total of 10 electrons. So there's 2 more negative charges than positive charges, which is why it has an overall charge of -2. Nitrogen will still have 7 protons, but because it has a 3-, that means that it gained 3 electrons. So now in addition to its 7 that it has 3 more, which means it has 10 electrons. So now that's why it's overall a negative charge. Okay, the proton number stays the same. It's the electron number that's changing. If we look at calcium, calcium has 20 protons under normal circumstances. Now calcium 2+ will also have 20 protons, but the +2 here means that it lost 2 electrons. So rather than have 20 electrons, it has 18 electrons. So there's 2 more positive charges than negative charges, which is why it has an overall charge of +2. And you can probably explain that using the same logic for aluminum 3+. You can try that out and then check with me if you are having any issues with that. So let's go take a look at why elements want to form ions to begin with. Why not just stay neutral? So first you need to know is that the goal of any element or atom is to become as stable as possible, meaning to become unreactive. They don't want to react anymore. They want to basically retire and be happy. So the most stable elements, which you all know now, are in group 18. They're the noble gases. And the reason that these noble gases are so stable, and you probably guessed it, is because they have a full valence shell. They have the 8 electrons in their last shell, or 2 for helium, but that's okay. It's a full shell on the first shell. So every atom wants to be like the noble gases. They want to have a full valence shell. Having a full valence shell is called a noble gas configuration. Sometimes we call it a stable octet, meaning they're stable because they have 8 electrons in the outer shell. Oct meaning 8. Now, that stable octet term applies to all the noble gases, to anything that has a full valence shell, except for really helium. It still does have a stable configuration. It's just you wouldn't really call it a stable octet because there's only 2 electrons to make it stable. So let's take a look at how elements will proceed to become stable. We'll start off with metals. Metals want to be like a noble gas. They'll actually try to be like the noble gas that comes before them, that precedes them. Precedes them means comes before them, by losing electrons. So metals will lose electrons. They'll become positive, and they'll be similar to the noble gas that came before them. So for example, if you look at lithium, its atomic number is number 3. The noble gas that came before lithium was helium. So it's going to lose an electron to be like helium. And when I draw these out, you'll understand what I mean. Non-metals are going to try to be like the noble gas that comes after them, so that precedes them. And they're going to do that by gaining electrons. So if you look at fluorine, fluorine has atomic number 9 in the periodic table, it's going to gain 1 electron, and it's going to look like neon. When it gains that 1 electron, it becomes negative, but it's stable now because it has a full valence shell. So again, I just want to recap what reactivity and stability mean. Noble gases are the most stable elements. That means they don't react very much. And the reason they don't react very much is because they have a complete collection of valence electrons already. They don't have to go hunt for any more. Okay? So being stable basically means you're unreactive. Whereas other elements that don't have a full valence shell, they want to try to gain or lose electrons. They're doing that by reacting. They're reacting with other elements to take their electrons away, or they're giving their electrons to other elements, so that makes them reactive. So anything that doesn't have a full valence shell is going to be more reactive than something that does have a full valence shell in terms of hunting or giving away electrons. So we're going to learn how to draw Bohr-Rutherford diagrams for ions. Here we have a Bohr-Rutherford diagram for the sulfur atom, the neutral sulfur atom. You can count the electrons. There are 16 electrons, and there are 16 protons. That's how I know it's neutral. They would cancel each other out, these 16 electrons and 16 protons. So what we need to do to figure out what type of ion a non-metal will form. Right now we're looking at non-metals. So for example, this is sulfur. It's a non-metal. You have to figure out how many electrons it needs to get a full valence shell. So the charge of a non-metal is going to be equal to the number of electrons it needs to have a full valence shell. So I want you to examine the sulfur Bohr-Rutherford diagram on the left and take a look at how many valence electrons it has. You can see that there are 6 valence electrons. That means that it needs 2 more electrons to fill this shell. So to draw the ion, what you do is you add those 2 electrons. So I'm going to add them in as an X so you can see that I'm actually adding in the electrons, and you should do the same thing. So we're going to add in an electron there and there as well. So now this is a sulfur that has gained 2 electrons. To show that it gained 2 electrons, we need to draw these square brackets around it and indicate its new charge. Since it gained 2 electrons, it's going to have a charge of -2. So sulfur requires 2 electrons in order to form a stable octet. You add 2 electrons to form the ion. Then you add the brackets, and then you put the charge on the top right. So if it gained 2 electrons, it's -2. If it gained 3, it's -3. But sulfur only needed 2. Because it only needed 2, it's going to gain those 2 and become a charge and have a charge of -2 in the end. So this here is an anion. Nonmetals gain electrons, and we saw that with this example over here. If a nonmetal needed 1 electron, you just add 1 electron and put a charge of -1 on top. If a nonmetal needed 3 electrons, you'd add the 3 electrons and then put a charge of -3 on top. Let's go take a look at a metal now. Here we have sodium. Sodium has 11 protons and 11 electrons. Sodium is a metal. So we also want to see what it needs in order to get a full valence shell. you'll notice that sodium has one valence electron. And here's what I want you to get. To have a full valence shell, to complete the shell that we're currently looking at, it needs to go hunt for 7 more electrons. That's difficult to do. So there's an easier trick for sodium to pull here. Rather than get 7 electrons, it could lose 1 electron. If it loses this 1 electron over here, we'll now only have this second shell left, and you'll notice that this second shell is full. So metals will lose an electron to become stable, to become like the noble gases. So proton number will stay the same. Neutron number stays the same. What we're doing now is we're drawing the sodium ion. Here's the first shell. I still have 2 electrons on that. Here's the second shell. I'm going to have 8 electrons there. And I'm not going to draw on the last shell because I lost the electron, so that shell is no longer there. So it's easier to lose 1 valence electron than it is to gain 7. Now, because this lost 1 electron, you need to indicate that it's charged. So you put the square brackets and you put a plus on top. Now, you could put +1. You don't have to put the 1 in. If there's no number there, that means that it's +1. Okay? So we know that the element to the left is sodium. I knew that because there are 11 protons. As soon as you see 11 protons, you can go look at which atomic number corresponds to that, and that would mean that it has to be sodium. How many protons does the ion have? Well, the ion has 12 protons because proton number does not change. Okay. Sorry, I shouldn't have said 12. I should have said 11. 11 protons because proton number does not change. How many electrons does the ion have? Well, we lost an electron. So initially, sodium had 11 electrons, but because we lost one, there's now 10 electrons left. This ion is a cation. And if you were to write the symbol for this ion, you'd simply put Na with a plus on top because it lost 1 electron. So metals lose electrons to become stable. If it lost 2 electrons, you would have taken away the 2 electrons. In the square bracket, you would have put a 2 plus. If it lost 3 electrons, you would have taken away the 3 electrons and put a 3 plus to the top right of the square bracket. Okay, so you can see over here that basically if you only have 1 valence electron, you'll become +1. 2 valence electrons, you become +2. 3, you become +3. Because when you think about it, it's easier to lose 3 than it is to find 5 somewhere. It's easier to lose 2 than it is to find 6 somewhere, and it's easier to lose 1 than it is to find 7 somewhere. However, if you have 5, it's easier to gain 3, so you become -3. If you have 6, it's easier to gain 6 than to lose 2. To gain 2 than to lose 6, so you become -2. If you have 7, it's easier to gain 1 than to lose 7, so you become -1. And as you know, if you already have 8 valence electrons, there's no need to gain or lose electrons, so usually noble gases won't form ions. And also, an interesting concept is, what if you have 4 valence electrons? Is it easier to gain? Is it easier to lose? And at the moment, I just need you to know that something with 4 valence electrons is not really going to gain or lose. It's really going to participate more in, let's say, sharing electrons. But that's all you really need to know for now. I'm not going to ask you to draw ions for anything with 4 valence electrons. So we're going to do a few practice problems together. We're going to try to draw ions for magnesium and for fluorine. So we're going to start off with the fluorine ion. If you look in your periodic table, you'll notice that fluorine looks something like this. So it's an atomic number of 9. So we'll start off by drawing the normal fluorine. just the one that didn't gain or lose anything. We know it has 9 protons and 10 neutrons. And it's also going to have 9 electrons. So 2 on the first shell. And 7 on the last shell. So we know that fluorine is a non-metal. Because it's a non-metal, we know it's going to gain electrons, but let's just take a look at that in terms of the electron number. On the last shell, fluorine is in group 17. It's a halogen. So on the last shell, we know there are 7 valence electrons. It's easier to gain 1 than it is to lose 7. So when we draw the ion, we're going to redraw everything exactly as we see it here, but we're going to add an electron. So proton number stays the same. So this is the fluorine ion we're drawing right now. 9 protons still, 10 neutrons, and then we have 2 electrons in our first shell, and now we're going to draw our last shell with the extra added electron as an X. And then because we gained 1 electron, we know we're going to become negative, so we put square brackets around the ion. And we put negative. You could put 1, or you can just leave it as negative, because when there's no number there, it's an implied 1. So here we have an anion, the fluorine ion. Now the interesting thing about nonmetals is when they become ions, their name changes. So the fluorine ion actually becomes fluoride. Fluoride. So nonmetals, when they become an ion, their name changes. Usually replace their ending, change their ending to "ide." So oxygen would become oxide, fluorine becomes fluoride, chlorine becomes chloride, nitrogen becomes nitride, and we'll learn those rules later on, but it's just a little tidbit of information to get you prepared for what's coming next. So again, the first step would be to draw the normal Bohr-Rutherford diagram, then take a look to see how many electrons you would be adding or removing. In this case, because we have a non-metal, we'd be adding an electron, only 1 needed in this case, so that would give us a charge of -1. Now let's go try a similar example, but this time we're going to do the example for a metal. We're going to try it for magnesium. So if you look in the periodic table, magnesium has a mass of 24, and it has 12, an atomic number of 12, so that means it has 12 protons. So we'll draw our nucleus here. 12 protons, 12 neutrons, and it also has 12 electrons, assuming it's the neutral atom. So 2 on the first shell, 8 on the next, and on our valence shell we have 2 electrons for a total of 12. So we know we have a metal here. So metals, like I said, they lose electrons to become stable. We just have to see how many electrons it has to lose to get rid of the valence shell. Over here we can see magnesium has 2 valence electrons, so it has to lose 2 electrons. So to draw the magnesium ion, we simply redraw the same nucleus, because protons and neutrons will never change. Now we're going to draw the electron shells, except for the last one because we lost 2 electrons. Now because lost 2 electrons, it's going to become positive, specifically positive 2. And what we're going to have to do is represent that using those square brackets. So remember, when you're losing electrons, you can only lose the electrons on the valence shell. You're not going to lose any of the other electrons. It's not up to you to choose that. So square brackets, and then it lost 2 electrons, so it's positive 2. When metals become ions, their name doesn't change. So this magnesium ion, this cation here, it's still magnesium, we're going to call it. Non-metals, you change their ending when they become ions, so fluorine becomes fluoride. Metals, their ending stays the same. So our first step again is to draw the regular Bohr-Rutherford diagram for the neutral atom, and then figure out if you're losing or gaining electrons, and afterwards redraw the Bohr-Rutherford diagram with either the gained electrons or the lost electrons removed, and then put the square brackets to indicate the charge that it'll become. So you should try the magnesium example again yourself, see if it matches what I did in the previous slide, and you should do the same thing for the fluorine example as well. Retry it, see if you get the same answer that I did on the previous slide. So just very quickly, I want to go over something called the ionic notation. We learned about standard atomic notation, where you write the symbol of an element, its atomic number on the bottom left and mass on the top left. The ionic notation is basically the same thing. It's just that if you have the ion, you put the charge on the top right. So for example, let's say I had calcium. Normal calcium, or neutral calcium, sorry, would have a mass of 40, an atomic number of 20, but if it was charged, it would have a charge of positive 2, so I just put positive 2 on top. And this is the ionic notation. So if you write this down, you know that you have calcium with 20 protons still, 20 neutrons. It's just that rather than having 20 electrons to give you an overall charge of 0, it has 18 electrons because there's 2 more positive charges. So this thing lost 2 electrons from what it originally had. Okay, so again, just to restate that, calcium you can tell has, if it was neutral calcium, would have 20 electrons and 20 protons. But when it becomes positive 2, what actually happened is that it lost 2 electrons. So now it's down to 18 electrons. It lost negative thought, so it became positive, but it still has 20 protons. So there's 2 positive charges more than there are negative charges. Okay, so for any ionic notation that I ask, you simply do the standard atomic notation first and then add the charge to the top right. So you should try practicing with aluminum. You'll have to figure out what charge it will become, and then you can proceed to draw the ionic notation. You can do the same thing for oxygen, figure out which charge it will become, and then do the ionic notation. Another type of ion we need to discuss just briefly, we're going to see it in more detail later on, is something called a polyatomic ion. So let's add this word in here, polyatomic. Poly means many. And so a polyatomic ion is basically a group of atoms that stick together and have an overall charge. So for example, over here we have phosphate. There's 1 phosphorus and 4 oxygens with an overall charge of 3-. This is not a compound, it's just an ion. To actually form a compound, the polyatomic ion would have to connect with some metal. So for example, here we have potassium connected to the polyatomic ion called nitrate, which is NO3-. We're going to work with these polyatomic ions in more detail later on. For now, just know they're groups of atoms connected together with an overall charge. They kind of act as one, and they have an overall charge. Okay. An interesting application is if you're a fan of hot dogs, you'll notice that they have a nice bright red color. That's what attracts you to the packaging or to the food itself. The reason that it has that nice bright red color is because there's lots of nitrates in there and nitrites. That's what gives the hot dog that red color, and also other processed and preserved meats will have those nitrates and nitrites in them. They're not necessarily good for you either. Look it up. So your task is to draw the Bohr-Rutherford diagrams for the first 20 ions in the periodic table. I know it's tedious. We're going to learn an easier way to do this later on, but the first 20 ions in the periodic table, you need to practice. Try figuring out what the charges will be. Try it for the metals and the non-metals. Okay? go take a look at the periodic table where you drew the 20 neutral atoms and use that as a basis to determine what type of ions and charges will form in this periodic table over here. The last concept I want to go over with you guys is the term isoelectronic. And so we discussed this earlier. I talked about how metals will lose electrons to become stable, to become like a noble gas. And when they do that, they become like the noble gas that came before them. So they look like the noble gas that came before them. So let me just show you an example. Sodium, we know, loses one electron, and it becomes sodium plus, so Na plus, becomes +1. When it does that, it actually looks like neon. So let's take a look over here. We know that sodium has 11 electrons, so there's 11 protons. I'm going to leave neutrons out right now just to focus on protons and electrons at the moment, and 11 electrons. So this is just the regular sodium, uncharged neutral sodium. Electrons. One on the outer shell here. When it becomes an ion, it's going to lose that one electron here, and it's going to look something like this. So again, I'm just focusing on the protons right now. You need to draw neutrons when you're doing this. So rather than have 11 electrons, it's going to have 10 electrons now. With our positive 1 over here. You know what, I may as well just add the neutrons in there for the sake of completeness. So this sodium now actually looks like neon. If you draw neon out, neon has 10 protons, 10 neutrons, and 10 electrons. Now it's not charged because it didn't lose or gain. But the point is that Na plus has the same electronic configuration as neon, meaning it has 10 electrons. And that's what we refer to as isoelectronic. An ion that is the same electronic configuration or electron configuration as another element. So metals, like I said, they're going to lose electrons and become like the noble gas that came before them. So sodium's number 11 in the periodic table. The noble gas just before sodium is neon, which is number 10. And so the sodium ion, other than its charge being +1, has the same number of electrons as neon. So we would say the sodium ion is isoelectronic to neon. Oxygen, on the other hand, gains 2 electrons. So non-metals, they gain electrons and they become like the noble gas that comes after them, that follows them. Okay, so oxygen has atomic number 8, neon has atomic number 10. So the noble gas that comes after oxygen is neon. Oxygen is going to become kind of like neon when it becomes an ion. So over here we have oxygen with 8 protons, 8 neutrons, and 8 electrons in its uncharged state, in its neutral atom form. So 6 electrons on the valence shell. We know that oxygen needs to gain 2 electrons to have a full shell, so we're going to do that now. Its proton number and neutron number, they're going to remain the same because those never change. And all we're going to do here is we're going to add the 2 electrons as x's. Here's one of them. And then we're going to put a bracket to show that it becomes -2. Now I'm not going to redraw neon, but you can see that oxygen now has 10 electrons, like neon does. So oxygen, the ion, is also isoelectronic to neon. Okay? Lithium, in the first slide that we discussed, would lose 1 electron to become like the noble gas before it, which is helium. So you should go at your periodic table and take a look at what these elements are isoelectronic to when they become ions. So if we take a look at, let's say, nitrogen, it has 5 valence electrons, so it's going to gain 3 electrons and become like neon. It's going to have 10 electrons like neon. Let's look at phosphorus on the other hand. Phosphorus, in group 15, has 5 valence electrons. It's going to gain 3 to become like argon, the noble gas that comes after it. But let's take a look at the metals. Beryllium, in group 2, has 2 valence electrons. It's going to lose those 2 and become like helium, the noble gas before it, right? 2 is before 4. Magnesium has 2 valence electrons. It's going to lose those 2 and become like the noble gas just before it, which is neon, right? You have 12 over here. Let's go back 1. That's 11. That's sodium. And the noble gas that we land on is neon. Okay. Calcium. Calcium is in group 2. It's going to lose 2 valence electrons to become like argon. Potassium is also going to become like argon, but it's going to do that by losing 1 valence electron. What will aluminum become like? What will gallium become like? What about sulfur? What about bromine? Try to figure those out using the same logic that we just discussed. Over here is our slide of homework. You should attempt all these problems. Use your notes to provide all the necessary keywords that you need to answer these short answer questions. This question over here requires you to predict what type of ions will form from the following elements. And this is a question where you need to communicate. So use all your keywords to communicate an answer to this question. In this table here, you just have to determine the number of protons, electrons, and neutrons, or write the ionic notation. So I'm going to do one example with you. If we look at this first example over here, we have nitrogen with its mass of 14, its atomic number of 7, and a charge of 3-. So this is the ion we're looking at. So we know from the atomic number that nitrogen has 7 protons, and we know from 14 - 7 there are 7 neutrons. Now normally, if nitrogen was neutral, there'd be 7 electrons. But because this is 3-, that means it gained 3 electrons. So now it has a 7 that it started off with plus the 3, that's 10 electrons. You have to take a look at which noble gas follows nitrogen to figure out what it's isoelectronic with. So it gains 10 electrons. That's similar to the previous example where we saw neon also has 10 electrons. To figure this out, you may have to draw out the Bohr-Rutherford diagram or simply take a look at your periodic table to see the position of the different noble gases compared to the element that you're studying. Okay? And sometimes you'll have to work backwards to figure out what element you're dealing with to figure out the standard ionic notation.